Hello and welcome to the webinar. My name is Chandimo Yunage and it's my pleasure to take you through the contents of today's webinar. Today we are going to discuss about noise reduction and power electronics design for automotive devices. Before I start, let me briefly introduce our group company. Cybernet Malaysia is a fully owned subsidiary of Cybernet Systems Company Limited headquartered in Tokyo, Japan. Established 37 years ago in 1985, Cybernet's partnership with Ansys is as old as the company is. We have sales subsidiaries also in China and Taiwan. You may have heard about Sigmatrix, MapleSoft, and Noises solutions. They are also actually a part of Cybernet Group. Cybernet Systems Malaysia supports customers in the ASEAN region. We are a channel partner of Ansys in those countries. Cybernet Systems Malaysia specializes in CA solutions, digital transformation, and we also provide engineering services, training, and consultation in those domains. With that introduction, let's move to our main topic for the day. Please also don't forget to send all your questions in the chat so we can send you the answers. I would like to thank Yanagi Akio-san and Koakutsu Shinobu-san of Cybernet Systems Japan for providing the original content analysis examples for this webinar. Ansys software used in this presentation are mainly the Ansys electronics products such as Ansys Maxwell, SI-Wave, Q3D Extractor, HFSS, and Ansys IcePack. These are the key areas we are going to discuss today. Firstly, we will review various items and elements required for automotive electronics design. And among many other interesting topics, we will introduce noise reduction for circuits and printed circuit boards related to ECUs and communication devices, as well as design solutions for power electronics. The electrical design technologies required for automotive include communication, motors, and noise reduction of circuits and printed circuit board systems. Automobiles are being equipped with various latest technologies such as electrification, ADAS or advanced driver assistance systems, and 5G communications. And these are being installed in the form of in-vehicle devices such as ECUs, advanced communication devices, and high-speed digital devices. The units in each area must be highly controlled by ECUs, and the noise reduction is an important factor in terms of quality and standards. Let's look at our noise reduction solutions for PCB systems first. Ansys electronics products allow integrated signal analysis, power supply IR drop, impedance analysis, and signal noise analysis as shown in the figure. In addition, Ansys electronics products can be integrated with EMI analysis and thermofluid analysis that simulates CISPR 25 standards. This is an example of vertex file signal analysis using Ansys SI-Wave. The wiring shown in red on the left side image is the target of the analysis. First, the entire PCB is analyzed by electromagnetic field analysis, and then circuit analysis is performed automatically. The IC at the center of the upper right image is the S-parameter model of the specified wiring, and the EBIS model is placed on the left and right. The result of the analysis is the waveform in the lower right image. Ansys SI-Wave can analyze EMI in the same environment. The figure at the top shows the EMI waveforms for the 3-meter far field, and the figures at the bottom shows the electric and magnetic field contours for the near field. You can see that the influence of electromagnetic fields is spreading in the vicinity of the wiring that is being analyzed. To reduce these noises, we will add a 47 ohm damping resistor to the wiring. Here are the results of the analysis. The top right image of 3-meter far field shows that EMI is reduced after adding a resistor. At the bottom, electromagnetic field contour diagram shows that the influence of electromagnetic fields on the surrounding area has been reduced. Even though it's not shown in this case study, there is a close relationship between signal stability and power supply stability. In general, a high abyssal source impedance increases the power supply noise and makes the signal unstable. For this reason, it's important to check the power plane impedance before performing a high-speed signal analysis. This is a case study of a three-dimensional electromagnetic field analysis using Ansys HFSS. The two boards are connected by a flexible cable and placed inside an enclosure. An external connection cable is also connected from the boards to the outside of the enclosure. The actual analytical model is shown on the right-hand side. In 3D analysis, due to the load on the PC and analysis time, it's a technique for efficient analysis to limit the wiring of the boards to be analyzed as much as possible. Here are the results of the analysis. The upper left graph shows peaks at 276 MHz, 772 MHz, and 952 MHz. Looking at the results of the electromagnetic field analysis, it's possible to see where the factors contributing to the respective peak frequencies are located. As countermeasures to reduce these noise peaks, we have changed the position of the flexible cable, added shielding, and added screws around the connector and on the board ground. These are the results after countermeasures were applied. You can see that the noise peak has been lowered and the electromagnetic field radiation level has also been reduced. By visualizing and examining electromagnetic fields in this way, it's possible to confirm the effectiveness of countermeasures before making any design changes. Ansys HFSS also comes with a model based on CISPR 25 standard that simulates site tests for conducted and radiated emissions. As in the signal analysis introduced earlier, a radiated noise can be obtained by circuit analysis of the S-parameter model with electromagnetic field analysis. This is an example of conducted noise analysis using Ansys Q3D Extractor and Ansys Simplorer. The figure on the left shows a power supply and switching circuit using IGBT transistors and IPMs, modeling the physical geometry of transistor connectors, bus bars, and cables. To compare the analysis results with the CISPR standard, the listen circuit is connected in the upper left corner. The figure on the right shows the analysis results. It shows the common mode and differential mode noise observed as the listen end. This conducted noise analysis is a practical example that many of our customers have used to good effect. Let me explain a few more details here. This is a diagram that summarizes the modeling. The package structure is modeled as a dynamic equivalent circuit or state space model and integrated with the circuit for analysis. The upper left is the results of the circuit analysis showing no significant noise. The upper right is the result of analysis with various structures connected. Spikes can be seen during switching. By adding elements closer to the actual product, which cannot be obtained from circuit analysis alone, verification before prototyping can be performed more efficiently. Here is the comparison data between the simulated analysis results and actual measurements. As you can see, the results are in pretty good agreement in general. Here is the results of the virtual measures. Yellow is the result with the filter added, and red color is the result with the filter and shield measures. In addition, we have recently released a tool called EMA 3D Cable, which enables easy creation and analysis of cable models when cables creates a noise problem. If you are interested in this tool, please feel free to reach out to our team. From now on, we would like to introduce you to our design solutions for power electronics. In today's power electronics system design and analysis, it's essential to evaluate 2D and 3D physical models and take a multi-domain approach including circuit, control, and power element models, as well as addressing thermal issues. We are going to look at some examples of how Ansys electronics products can be applied to the field of power electronics, such as cables, bus bars, actuators, sensors, and thermal analysis of PCB. First, I will show you an example of cable bus bar analysis. Cables and bus bars are used to safely transferring power or signals from a power or signal source to a load. The design of cables and bus bars requires electromagnetic field analysis to calculate parameter values for resistance, inductance, and capacitance for the geometry and material property values. In addition, it is essential to work with circuit and system simulation to verify system operation because it's necessary to consider whether the target system operation can be achieved, and also the coupling of noise from each operation when signals or power are supplied to several different objects through branches. Here is an example of analysis of motor drive characteristics including cables. Using Ansys 2D extractor, the frequency characteristics of the cable resistance, inductance, and capacitance are modeled by electromagnetic field analysis of the cross-sectional shape of the cable, as shown in the lower left of the slide, and combined with system analysis in Ansys Simplorer as a state space model to evaluate motor drive characteristics considering parasitic components of the cable. The lower right shows the time required for the motor to reach the target rotation speed with and without the cable model, and it can be seen that the time is longer when the effect of the cable is taken into account compared to the circuit alone. In this way, combining the system simulation and cable characteristics makes it possible to study motor drive characteristics that are closer to actual behavior. The next example is an analysis of a power supply system for vehicle heaters, including bus bars. A state space model that simulates the frequency characteristics of the bus bar's resistance, inductance, and capacitance obtained from an electromagnetic field analysis using Ansys Q3D extractor is combined with a system simulation in Ansys Simplorer to evaluate the bus bar's effect on the system operation. Shown to the right is a circuit system with a bus bar inserted between the battery and the heater electrical load model. Looking at the current supplied to the heater, shown in the lower right, we can see that the desired current is not reached within the pulse drive time due to the RL time constant of the bus bar. Next, it can be observed that the drive current on the electrical load side has a ringing noise due to coupling of the switching pulses of the heater. Thus, by verifying the system considering the parasitic component of the bus bars, it's possible to verify at the design stage those aspects that cannot be evaluated by circuit simulation alone. Next, we will show an example of electromagnetic actuator analysis. An electromagnetic actuator or solenoid operates by generating an electromagnetic field to move an armature a given distance with a certain force. Since the armature is moved by magnetic force and the magnetic force changes with the movement, the analysis must include magnetic field including transient motion effects. In addition, it's necessary to conduct an analysis that includes the balance with structures such as springs and dampers to capture phenomena that is close to real situation. Characterization and modeling is performed in Ansys Maxwell by performing transient magnetic field analysis using 2D and 3D geometry of an electromagnetic actuator. As a result, as shown in the lower left of the slide, you can see how the magnetic flux density and flux state changes depending on the position of the armature. Furthermore, by coupling the Ansys Maxwell magnetic field analysis model with the Ansys Simplorer system simulation, The electrical, mechanical, and hydraulic load domains are linked to simulate conditions as close to actual operation as possible to verify the validity of the system. This analysis allows for nonlinear saturation, AC magnetic fields, and motion-induced eddy currents, counter EMF or back EMF, and time variations of the magnetic field to be considered. These are some examples of sensor analysis. Many magnetic sensors are used in power electronics equipment and systems. This includes resolvers that detect the pace angle of motors, variable reluctance sensors that detect wheel speed, flux gate sensors that detect overcurrents in bus bars, eddy current displacement sensors that detect cylinder defects, etc., and Hall sensors that detect the rotating position of wheels. For the design of these sensor components, magnetic field analysis, including the sensor part and the state of the observed object, is indispensable. Here is an example of analysis of a variable reluctance sensor. In a variable reluctance sensor, the fixed magnetic field of a permanent magnet changes its magnetic flux as the object that is being analyzed approaches or passes by, and the coil detects the intensity changes and outputs a voltage value corresponding to the speed. Ansys Maxwell is used to analyze the magnetic field by combining the sensor and the wheel of the observed object. The sensor part consists of a permanent magnet, a coil, and a pole piece. This sensor part is combined with a rotating wheel to observe the time variation of the chain flux, excitation voltage, and magnetic flux density with respect to the state of the target object. Finally, we will show an example of thermal analysis. In power electronics applications, design rules for temperature are usually defined by the required specification. To keep the design within the ideal temperature range, thermal analysis is required to verify heat generation due to electrical losses, heat exchange with bounded temperatures due to thermal impedance, and cooling effects of heat sinks, fans, etc. In this section, we introduce thermal analysis using a PCB as an example. The electrical loss calculated from Ansys SI wave DCIR drop analysis can be passed to Ansys iSpec as joule heat information to determine the temperature conditions on the board. Furthermore, Ansys iSpec can efficiently verify the effects of the case that holds the board, ICs that are heat sources on the board, heat sinks for the heat dissipation, cooling fans, and grills for air ventilation, and the effects of natural or forced air cooling. It's possible to design within the given temperature range of the required specifications. So these are some of the takeaways from today's webinar. We explained a simulation for automotive electrification in the areas of PCB systems and power electronics. With electrification, there is a great opportunity to propose electrification technology or ECU control for related parts such as shock absorbers, steering systems, etc., as well as technology development corresponding to advanced driver assistance systems or ADAS. We also mentioned that noise reduction and power electronics control of complex systems is becoming increasingly difficult. Finally, we would like to emphasize that Ansys Electronics products are keeping pace with these product developments, enabling applications for new technology developments and innovation. As I mentioned at the beginning, we will reply to all the questions after the webinar by email. If there's anyone who could not drop their questions in the chat, please send an email to information@cybernet.asia. So with that, we have come to the end of today's webinar. I hope you found it interesting. If you need further information or demonstration of today's topics, please feel free to reach out to our team anytime. You can call us, email, or send an inquiry using the web form on our website, www.cybernet.asia. Thank you and stay safe.